Jai Hind everyone. I am Nikita Jaiswal from Civil Engineering Department, Ajay Kumar Garg Engineering College. Today I am going to teach you about fluid mechanics. The important topic here I am going to take is properties of fluid. So the properties of fluid is actually the base of complete fluid mechanics engineering, because without knowing the properties of fluid, you know what kind of any particular fluid or liquid or gas, what kind of properties they possess. Without knowing the property, without knowing the base of fluid, you cannot go further for analysis, for design, or any kind of fluid mechanics engineering prospects. Okay, so we are going to discuss the first properties of fluid, and so the first introduction, we need to discuss what is fluid, how this is differ from solid, what kind of deformation we need to discuss, we need to study in particular case of fluid. So the first is we are going to understand. The first is the properties of fluid and fluid statics. So fluid mechanics is basically the study of behavior of fluids, either at rest or in motion. When a particular fluid is in a rest condition, the type of engineering we say it is fluid statics. And when the particular fluid is in motion and we are studying it, so that kind of fluid mechanics, that will be called as kinematics or dynamics. In the case of kinematics, what we say, particular fluid is flowing, particular liquid is flowing, but we are not considering what kind of forces are involved in that particular flow, what are the causes of the flowing fluid. So when we are not considering what forces are actually responsible for the flowing of fluid, then the branch of fluid mechanics is called as kinematics. But when we are considering, the called as your fluid dynamics. Okay. Now the analysis of whole fluid mechanics is based on some fundamental laws. As we know, there are some fundamental laws, that is continuity of mass and energy with force and momentum. We very much we know what is the impulse momentum equation, what are the forces involved in particular flow with velocity, with acceleration. So whatever continuity of equations are involved in particular flow direction, so we are going to take in analysis of flowing fluid, such as continuity equation of mass, continuity equation of energy. So we will discuss further. Now the understanding of fluid at rest condition and in motion condition is actually very much important. The properties of fluid differ when they are in motion or in a rest condition. Usually when the particular fluid is in rest, we apply hydrostatic pressure laws, and we usually apply Pascal law for determination of different kinds of properties. Either the first important property is actually pressure measurement. We need to know what kind of pressure are involved, what kind of pressure intensities are involved in flowing fluid or in rest condition. So what kind of laws we are going to take in both the forms. So this is very very important. We need to understand the properties and behaviors of fluid, or in rest or in motion. So this is important. Now we need to understand what are the actually states of matter. So we very well know there are three phases of matter: is solid, liquid, and gas. Usually we take liquid and gas in a subset of fluid. Okay, and solid is a different. What are the difference between solid and liquids or gases? As we know very well, when the molecules are closely bounded together with each other, that particular mass is called as solid. When there is small forces between molecules, and the distribution is random, then the matter will be called as gas. And when we come to fluid, we know very well that it is in between gas and solid. So we will discuss what is liquid or what is fluid, how the behavior are changing with different aspects. So although differ in many respects, liquid and gases have common characteristics in which they differ from solids. Obviously, the characteristics of gases, fluid, they are differ from solid. And what are the characteristics? So we know very well, whenever we apply some kind of stress in any particular solid, what happen actually? That doesn't deform, that particular solid matter doesn't deform instantly. But in case of fluid or gases, when we apply shear stress, that deforms continuously. Whenever we apply a particular shear stress, okay, see, when in a static condition that particular fluid is placed here. For an example, when I apply a shear stress or kind of force, you say, that particular fluid will be deformed. Okay, maybe that some amount of fluid spills over here. So what I am trying to say is how the behavior of solids and liquid are differ. So the liquid and gases are fluids, obviously. In the contrast to solids, the liquid lack the ability to resist deformation. Because a fluid cannot resist deformation force, it flows under the action of force. Its shape will change continuously as long as the force is applied. Okay, the force, let's say the force is continuous. So what will happen? This particular fluid will deform continuously until the stage is reached when we are not able to apply the particular force on that. So what will happen? The water or liquid will flow over at some place, or maybe the position of fluid will not be at that particular point. So this happens. This is the basic difference between liquid and solid. So the solid can resist deformation force while at rest. The force may cause some displacement, but solid does not continue to move indefinitely. Okay, so the fluid, obviously the fluid flow under the action of such forces, we know very well, deforming continuously as long as the force is applied, and it is unable to retain unsupported shape. Whenever we put any kind of liquid in particular container, that liquid take the shape of container only. Okay, so this is how fluid differs from solid. And now we are going to understand when the fluid is in gaseous or liquid form, how the shear stress distribution, how the viscosity are going to differ. See, viscosity is also a very important property of fluid. We will discuss further. So solid can resist the applied shear by deforming, and stress is proportional to strain. We know very well, in case of solid, that applied stress is proportional to strain, but this is a case of solid. Okay, but when we take any case of fluid, the shear stress is actually proportional to strain rate. This is du by dy. Okay, this is actually your velocity gradient. You can say is as velocity gradient, you can say it as strain rate. So see here, in case of solid, okay, this is a case of solid where we are saying the shear stress is simply force divided by area. Okay, and what is the force? Whatever area on which the particular force is acting, this will be your capital A, and force in Newton what we are applying. So this is proportional to, as we have seen here, it's proportional to simple strain. Okay, so this is you can say an example. So two plates, in the one is force is applied and the shear stress developed will be force divided by A. This is this is an example of rubber. That rubber was particularly was actually in this shape, but after applying force, this is deformed by some strain alpha. Okay. Now here you can see this is our distribution curve, how that particular rubber is deformed. Okay. Now when we talk about fluid, this was about solid, and how we can analysis the deformation in case of solid. But when we go to fluids, actually there are two forces which are acting in between the layers of fluid. The first one you can say tangent to the surface, and second one you can say normal to the surface. Okay. So basically stress is what? Stress is actually defined as the force per unit area. Stress you can say is force per unit area. Now this particular force acting on, if we are taking in this figure, you can see we are taking an incremental, a small area. We are taking just an example of small area which is having area of del A, in which there are two types of forces are acting. The first is tangential to the surface, that is Ft, and the second one is normal to the surface. So these are actually components of forces acting on area dA. Okay. So what we said, stress is defined as the force per unit area. Now the normal component. What is the normal component? Here you can say the normal component is Fn. In fluid address, the normal stress is called pressure. Okay. So when we take, any fluid condition which is kept at rest, let us suppose we are taking any level. For an example, this is xx. Now I want to understand what kind of force will be acting on this particular layer in particular level. So whatever pressure will be coming on this xx level will be equal to pressure force, or you can say normal to the surface force or pressure. So this Fn is actually pressure, and how we can calculate pressure under condition of static fluid is simple. We can apply Pascal law, that will be equal to rho gh. Rho is what? Rho is mass of particular fluid, and g is what? This is acceleration 9.81, and h is what? It's actually a distance of this particular level from free liquid surface. Okay. So the force, the normal force acting at particular level, we can find out by using Pascal law, that will be equal to a rho gh. Okay. And the tangential component is shear stress. Okay. That shear stress, because of the concept of shear stress, we are further discuss viscosity. See, viscosity is what? Viscosity is simple. When we are studying any fluid, let us suppose we are taking two fluid layers. In between there are some viscosity. For an example, just let us suppose this particular first layer is having velocity of u plus del u, and the lower one having a velocity of u. Okay. Let us suppose these layers are separated by distance del y. Okay. So because of the velocity difference in that particular in between the particular layers, because of this velocity difference, there will be a existence of shear stress in between the layers. What that will do, actually that particular shear stress will try to induce a friction, that will resist the flow, that will resist the velocity of flow. So this is how we talk about shear stress. This is how the concept of viscosity introduces in case of fluids. So this is simple diagram where we are going to discuss how the liquid and gases are differs. So a liquid takes the shape of the container, as we discussed earlier, as it and form a free surface in the presence of gravity. The gas expands until it encounters the walls of the container and fills the entire shape available. Okay. And the gas and vapor are often used as synonymous words. Okay. Okay. Now we are going to discuss the category of fluid. The category, that particular category is actually related to shear stress. So what we have studied in previous slides, in case of fluids, actually shear stress is proportional to du by di, or you can say it as velocity gradient. Okay, this is, you can say, velocity gradient, or you can say it as shear strain. Okay, so this is how this equation is actually called Newton's law of viscosity. And you can see there is no term of viscosity. Now this will be solved further, like tau will be equal to mu du by dy. Here mu is called as viscosity, or you can say it as dynamic viscosity. Okay. So this is the equation. This equation is actually Newton law of viscosity. So what Newton law of viscosity says is, it is simple. Tau will be proportional to velocity gradient. In velocity gradient, how this velocity gradient is defined? That del u is the difference between velocity is different between velocity of two layers, and del y is actually the distance between the two layers. Okay, this is Newton law of viscosity. So that fluids that obey Newton law of viscosity, so this will be called as Newtonian fluid, which actually follows that particular equation. That particular equation says shear stress is proportional to velocity gradient. But when they are actually in existence, there are many kinds of fluids, okay, available in nature. So there are some fluids which actually follow Newton law of viscosity. There are some fluids which do not follow Newton law of viscosity. So fluids which do not obey Newton law of viscosity is called as non-Newtonian fluid. Okay. The viscosity of the non-Newtonian fluid is dependent upon the velocity gradient as well as the condition of fluid. What I have already said, that the viscosity, this particular viscosity, obviously it depends upon the velocity gradient as well as the condition of fluid. Now again, further explanation, Newtonian fluid is a linear relationship when there is a linear relationship between shear stress and the velocity gradient, or you can say the rate of shear. Okay. The slope is constant and the viscosity is constant. So we need to understand this two terms. What is the slope? What is the slope, which is we are saying it is constant, and the viscosity is constant. So we'll discuss it. Non-Newtonian fluids. The slope of the curves for non-Newtonian fluid varies. Now we will discuss how, see in this slide, this is this equation in Newton law of viscosity. Okay, here we have already understood what is del u by del y. Here mu will be called as dynamic viscosity of the fluid. Okay. Now we go further. Here you can see a particular graph between shear stress and rate of shear strain. Okay. Now here you can see the variation of shear stress with velocity gradient. It is simple variation between different kinds of fluid. Okay, that kinds of fluid may be Newtonian fluid, maybe non-Newtonian fluid, maybe ideal fluid, maybe pseudoplastic, maybe Bingham plastic, maybe dilatant. So there are another types of fluid which some of them do follow Newtonian law of viscosity, some do not follow. So here we are going to discuss this kind of fluids and how the curves or shapes of the particular fluids are different. So fluids obeying Newton's law of viscosity, for which mu has a constant value, is known as Newtonian fluid. In the previous slide, just a previous slide, what we are talking about, the slope is constant. Okay, so here you can see we have plotted particular you have plotted shear stress versus shear strain. Here you can see a straight line, this one, this is your Newtonian fluid, or you can say the slope is constant. The slope is constant, that shows that shear stress is proportional to du by dy or velocity gradient. So this kind of fluid is called as your Newtonian fluid. Other than this slope or this curve, all the other fluids will be called your non-Newtonian fluid. Okay, so most common fluid fall into this category, for which shear stress is linearly related to velocity gradient. Okay. Next is fluid which do not obey Newton's law of viscosity are known as non-Newtonian fluids and fall into one of the following groups. So now further we'll discuss how non-Newtonian fluids are different from each other and what are the types. Okay. The first is plastic. Okay. The shear stress must reach a certain minimum value, actually certain minimum value before flow commences. Here you can see the curve of plastic, the black one. Okay, here see when we want to we want to show, or we want some deformation, let us suppose. Okay, in that particular case of plastic, when we apply shear stress, when we apply shear stress, what we see, we are applying shear stress, but there is no deformation produced, but when we reached a certain point, then after that point deformation is produced like this. So actually this is called yield value or yield stress of particular plastic fluid. We have to reach at this level to produce deformation. So this kind of fluid where we need to cross yield value or some amount or some value for particular fluid. So this kind of fluid is called. So here the equation for plastic fluid is actually like this: tau equal to A plus B mu du by dy whole to the power n. Okay. For in case of Bingham plastic, okay, in case of Bingham plastic, actually n equal to 1. Okay. So this is the equation is actually basically for non-Newtonian fluids. Okay, when the n will be equal to n, then the plastic will convert it to Bingham plastic. The example of Bingham plastic is actually sewage sludge. Now the second is pseudoplastic. Pseudoplastic is simply kind of fluid in which then dynamic viscosity decreases as the rate of shear increases. So example of this kind of pseudoplastic is colloidal substances like clay, milk, cement. Okay, so there are different kind of fluids. The category of different kind of fluids depends upon the how viscosity is reacting with shear stress. Okay, In case of pseudoplastic, is actually viscosity decreases as the rate of shear increases. In case of dilatant substances, there are some other things like dynamic viscosity is actually increases with the rate of increase, shear is increase. For example, quicksand. In case of previous one, there was actually decrease in viscosity in pseudoplastic, but now in case of dilatant substances, this actually increase in rate of shear, increase in dynamic viscosity as well as increase in shear stress. Okay, the example is quicksand. Now the fourth is thixotropic substances. Again, the dynamic viscosity decreases with the time for which shearing force is applied. Okay, the fifth is rheopeptic substances. Dynamic viscosity increases with the time for which shearing force is applied. Then sixth one is viscoelastic material. This behaves similar to the Newtonian fluid, but if there is a sudden large change in shear stress, they behave like plastic. So there are different kinds of fluids. Some of them behave as Newtonian, some of them behave as non-Newtonian. Here we have seen 6 different types of non-Newtonian fluid. The other category in which we will deal also, the case or classification of ideal fluid. What ideal fluid is actually, it is not a real fluid. In this particular kind of fluid, we actually assume that that there is no viscosity between the layers. If there is no viscosity, that means there will be no shear stress. Okay, with no viscosity actually will induce zero shear stress. Okay, so but actually this is not a real case, but analysis of assumptions based on ideal fluid, still this is very much helpful in achieving some practically useful solution in analyzing some of the problems arising in fluid mechanics. So actually we use this concept in solving some complex problems. Although ideal fluid is not a real fluid, in this we assume that there is no viscosity between the fluid layers and also no shear stress. So there are some engineering units that comes with the properties of fluid. Obviously we know very much well what is mass, what is time, what is temperature, current, and this primary units will be useful in dimensional analysis actually, and these are other derived units. Okay, we need to understand, we need to know actually what is the force, what is the unit of force, what is the unit of energy, power, pressure, Pascal, density kg per meter cube, specific weight Newton per meter cube, relative density no units, viscosity Newton second per meter square. This is actually for mu, dynamic viscosity, and surface tension Newton per meter. So now we are going to discuss how we define different properties of fluid. The first one is density. The density of a substance is the quantity of matter contained in unit volume of the substance. It can be expressed in 3 different ways. First is mass density. Mass density rho is defined as the mass of substance per unit volume. Okay, simple. Rho will be equal to mass divided by volume. The unit will be equal to obviously kg per meter kg per meter cube. Okay, the dimensions will be equal to ml to the power minus 3. Typical values are defined as the most useful, we are going to use mostly the density of water will be taken as 1000 kg per meter cube. Okay, the second important property is specific weight. Specific weight is actually defined as the weight per unit volume. Since the weight is dependent on the gravitational attraction, the specific weight will vary from point to point. according to the local value of gravitational acceleration g. Obviously, at particular locations g are different, some other locations g are different. If acceleration, the velocity of g is changing, then obviously the specific weight of particular matter will change according to location. The relationship between specific weight and rho can be deduced from the Newton's second law. Here you can see specific weight is equal to rho g. This is very much important formula. This formula starts from here and will not end till unit 5. So units are Newton per meter cube, their dimensions and other values. Relative density. Relative density is actually nothing but specific gravity. Specific gravity you can denote it as capital G also. Here specific gravity is defined as the ratio of mass density of a substance to some standard mass density. You know, when we formulate specific gravity of any particular fluid, what we'll write as a mass density of particular substance or fluid divided by mass density of water at 4 degree centigrade. So mass density of water at 4 degree centigrade is actually standard mass density. Okay. We choose this value for our calculations. Okay. Okay, because this is a ratio of two same quantities, this is dimensionless, this is unitless. So here again there are two types of viscosity. The first we have already studied, the dynamic viscosity, tau divided by velocity gradient. Okay, so here this is called as your dynamic viscosity, can be defined as shear force per unit area that is required to drag one layer of fluid with unit velocity past layer a unit distance away from it in the fluid. Okay, so the unit is Newton second per meter square. Next is kinematic viscosity. What is kinematic viscosity? Is actually when we divide dynamic viscosity by mass density, this will be called as your kinematic viscosity. So the kinematic viscosity is defined as the ratio of dynamic viscosity to mass density. Okay. And the unit is meter squares per second, and there is another unit is Stokes, where you can say 10 Stokes is equal to 1 meter square per second. Dimension is L square T to the power minus 1, and typical values are shown here. So this is how the properties of fluid can be explained. This is how we can differ solids and fluids, and this is how this is actually the base, the starting of fluid mechanics. Without knowing all these factors, without knowing all these properties, we cannot go further for analysis and design of fluid mechanics, and we cannot we cannot even enter in the field of fluid mechanics. So that's all for today's lecture. Jai Hind.